Hello and welcome to the session FEM analysis. Here you will learn how to set up a FEM model and how to analyze it. You will define boundary conditions for a cantilever beam, which has a restraint and a force acting on it, and then analyze the deformation. This will help you to understand the structure of the individual steps of a FEM setup and how to assemble a runnable model. We need 4 different inputs for this lesson. One is the design space of the cantilever beam, which is a solid body, and if you would like to know how to generate solid bodies or geometry in general, please go to the geometry generation lesson. Then also we have these non-design spaces as an input prepared, and then we have 2 surfaces. One which the force will be applied to, here the front surface of the non-design space, and another one which will be fixed or supported, which is here this surface. To build up a FEM model and then analyze it, we have to first create solid parts, then define RBE elements, define the FE boundary conditions, and then lastly we can assemble and run the model. So we have 4 steps to go through. Let's start with the first one and look into the solid part creation. A solid part is a fusion of a mesh with material properties. And first we have to mesh the solid body, and in this case we have 2 inputs, the design space and the non-design spaces. So our input is a list of solid bodies, which you know because of this dotted line indicating it. And now we have to mesh our solid bodies using the Altair Hypermesh mesher. Type in solid mesh and you will get this component. Let's move it up a bit. And here you plug in the element size, also plug it into the minimum and maximum of interior size so that we get equally sized elements inside and outside, on the surface and also on the inside of the element. And then I would like to change the element type to quartz strictly, so that we only have quartz cells, and now this whole thing has to recalculate. Of course, you can use the drop down for different settings, and you'd use it again, and now we have a strictly quad solid mesh. In case you don't have an Altair license, you can use this internalized model and just use this for the next steps. Okay, now we have our solid meshes, and right now we have, let's plug in a panel here to check what we have. As you can see, we have 3 different meshes. The first one is the design space and then the 2 non-design spaces. And to now define the solid parts, I would like to split up this list because I want to define the solid parts for the design space and the non-design spaces separately. So I will use the split list component. Plug this in here and we will split it after the first index. So now we have a single data value flowing through here, which is the mesh of the design space. And then we have 2 solid meshes in here. You can of course connect a panel to check. Yeah, this is 1 mesh and here we have 2 meshes. Okay, great. This is what we are going for. So now we can actually create the solid parts. Okay. If you type in solid part, you get this component. You can just copy and paste it. So we need it 2 times. You can connect the names and then use the list A, which was the design space, solid mesh for this, and list B, which are the non-design space solid meshes for this solid part, and they both have the same material, which is steel. Just plug the material in here, and now we have two different solid parts defined. Just plug them into these outputs, and we are already done with our first steps. One more thing to know about the material: it's provided for you, so you don't need to worry about it at all, but it's important to know generally when you work on your own that the software is unitless, so you have to take care of what units your parts are in and adjust your values for example materials for those units. Let's continue to our second step, which is defining the RBE elements. Blend out the solid parts first. Alright, so we have this point here. You can see it. And this surface body, which is the front surface of the non-design space. I blend in the cantilever beam again so we can actually tell where we are in the model. Okay, so this is the surface and this is the point. And now we want to couple all nodes that lay within this surface to the point with rigid elements, and then later we will apply force to that point, but right now we just want to define those rigid elements that will couple the nodes to the point. So type in RBE and you will get the connector spider. You can of course also type in connector spider. We will name them force because we will later apply force to that point, and then define the target. As you can see right now, the component already works. We don't have to apply this point into the start node because right now the start node is the center of the target geometry. So this point here, oops, that point right now is our start node, and if I now plug in the provided point, you see that this now is our start node. And then we already have defined our elements. I will blend these out, and we can continue to the next step, which is defining the FE boundary conditions.